Okay. Hello, good afternoon, everyone. Today we'll have Dr. Adriaan from the Ecole normale supérieure de Lyon that will talk about Eutectic Solvents, 3 words that deserve some nuance. Thank you very much, Adriaan, for accepting our invitation, and share with us your knowledge.
I will be happy to. Thank you very much for the invitation. It took a while to actually accept because even though there is COVID going around, I managed to get another virus, but here we are. And luckily via the internet, it's possible to share this on a distance. So I will start if you don't mind. So indeed the title of my presentation is Deep Eutectic Solvents, 3 words that deserve some nuance, which is quite different from my thesis title, which was A New Generation of Designer Solvents. This was in 2018. In the meantime, I've gained some insights in the field of deep eutectic solvents that make me a bit milder about the big title of New Generation of Designer Solvents. So I think each of the words come with a bit of nuance, and I would like to start with the middle one. I think the one that everybody is the most familiar with here, which is eutectic. And even though, again, I think you're all familiar with it, I would like to still go through the formalities of what is eutectic phase behavior. And basically it starts when you mix the components. So it has to be a mixture of at least 2 or more constituents that are miscible in the liquid phase and immiscible in the solid phase, or both partially. And that means that there are really a lot of mixtures that qualify as eutectic. So they're very common, and this gives us also the opportunity of making a lot of eutectics. So that's good. Then, of course, this can be depicted in a phase diagram, where if you mix a bit of B to A, the entropy increases. That gives a decrease to the chemical potential of the liquid, which leads to a depression of the melting temperature of the mixture as compared to the pure component. And this happens also on the other side. And in the middle, or at the eutectic point, is the point where the mixture has the lowest melting temperature of all compositions. And that gives us these phase fields. So the completely miscible liquid at the top, the completely immiscible solids at the bottom, and 2 areas where the liquid is in equilibrium with the pure solids. And this is, of course, simple eutectic phase behavior. Then, if you want to use these liquids at a certain temperature for an application, you can draw a horizontal line, and at the operational temperature, you will get a range of compositions that are liquid for your application. So that was very quickly what eutectic is. Now, maybe the more interesting part, the deep. Well, there are some definitions in literature about what a deep eutectic solvent is. And I think one of the most shared ones is the one from Abbott in his review, where he says that deep eutectic solvents are formed from a mixture, a eutectic mixture of Lewis and Brunstad acids and bases, which can contain ions. Well, while I think this is in principle correct, I think it's also restricted to a certain type of components, while eutectic behavior is not. So maybe this definition is a bit too restricted for defining deep. And then there's also a definition that is very broad. In a recent review on the effect of water on ionic liquids and deep eutectic solvents, where it basically says that deep eutectic solvents are eutectic mixtures. And I think if we already have a term eutectic mixtures, we don't need another term deep eutectic solvents. So I think this one is too broad. And then there is also the definition that a lot of people adopt from the ionic liquid world, which is that the mixtures should be liquid below a certain temperature. In this case, it's 25, but there are also people that say 100 centigrade. And I think this is sad because these temperature boundaries, they're not really a property of the liquid itself. They're an environmental parameter that you use then to define the mixture itself. So I think it's better to look to properties of the mixture itself to define deep. So if we go back to where it started, the term deep eutectic solvent, it's this paper, where for the first time deep eutectic solvent was put in publication. And it starts actually with something that is nice, which already gives nuance. that eutectic mixtures have been used before to lower the melting temperature of mixtures containing salts. And that some of these gave rise to a deep eutectic. And that's good. It's even so good that you can use these mixtures at ambient temperature as a solvent. But the main property of this is that there is a significant depression of the freezing point. Well, you can also say melting temperature, freezing point. In principle, it should be the same, but experimentally it doesn't always have to be, but I'll come back to that later. But the most important is that it says here significant. But this is not the real beginning, of course. The real beginning of eutectic already started much earlier in 1884. Laura did some nice literature study and found the citations where actually the first time that eutectics were mentioned is found. And he says that the eutectic temperature is the lowest temperature of liquefaction of the mixture itself. So basically what I just showed, and that melting can be connected to solubility so that it's composition dependent. Then deep eutectics were also mentioned a very long time ago. There's, for instance, this paper from 1921, almost 100 years ago, where tiefer eutectics are described in German. And a bit more recent, from 1977, there's also Eutectic profond in French. Well, I'm in Lyon, so I should speak a bit of French. And they also show that the eutectic is surprisingly deep. And they do that with the phase diagram. And here they show also what you can expect if you have an ideal eutectic. So you can see that the real eutectic is much lower than the ideal eutectic. And that brings me to basically the definition that you already gave at the conference in Tours, and which was later on published in the solution chemistry, that eutectic temperature should be significantly lower than expected, and the expected is the ideal eutectic. And you can define it both in temperature and in ideality, but I like temperature better because it's something that you can directly measure. So the difference between the real and the ideal eutectic should be lower than 0. But the question is, how much lower is significant? And I won't give the answer here, but I do think that this is a discussion that should be held by both editors and reviewers for people that want to publish and in the reviewing process. But also when you're writing a manuscript, it should be stated there why you consider your eutectic deep. And if it's not stated, maybe we shouldn't call it deep. That's my opinion about the deep part. So all fun and games. We know now how to define this deep eutectic, but we should also be able to measure it. And in order to determine the depth of the eutectic as compared to the ideal eutectic, we need some information of the mixture, of course. First of all, the fusion properties of the pure components, which normally can be found in literature. And here are some suggested sources, but also if you measure them directly in the lab. And I always like to do that because it's not said that the components that you have in the lab are as pure as the ones in literature or the other way around. If they don't melt, and there are quite some components that do not melt before they decompose, including chlorine chloride, one of the archetypal components, it has to be derived indirectly from other data. And for instance, from the phase diagram, as you did in 2017, or from the mixing enthalpy, which some other group did in 2016. So these are approaches to still get fusion properties, even though they're experimentally inaccessible. And these are, of course, apparent fusion properties. They don't really exist, but you do need them in order to describe the eutectic depth. So phase diagram data is the second part that you could read. And also this is not necessarily very simple. In principle, the measurement of a phase diagram is quite straightforward. But as you can see, for the most known deep eutectic solvent, urea with chlorine chloride, the data is already quite scattered, especially around the eutectic composition. And this is also because there are a lot of different methods to measure these deep eutectic solvents phase diagrams. And each of these methods have some advantages and disadvantages. So I want to distinguish between methods that use a dynamic temperature and a static temperature. With a dynamic temperature, you keep the composition constant and you move up in temperature or down, and you check where the phase transition is. This can be done with capillaries, a hot state microscope, solid equilibrium cells, or colorimetric with the DSC. And you can see here the hot stage microscope and the DSC, and some others have also DSC, and Abbott used just a visual approach. So these are all methods that use the dynamic temperature. The problem is that not always the crystallization of your sample goes very smoothly. And this can give trouble when you change the temperature up and down. So another approach is to, instead of keeping the composition constant, keep the temperature constant and just change the composition by making small additions of either solid or liquid to the mixture, and check where the liquid either becomes clear or forms particles, so a cloud point. And another approach is the centrifuge method that we developed in Eindhoven, where we can also measure the difference, the equilibrium between the liquid and the solid by simple phase separation with centrifugation. That's all described in this paper. Then another thing that affects the phase diagram a lot is the addition of a third component that is either wanted or unwanted. And one of the most common components that does this is water, because a lot of components from the eutectic solvents are hygroscopic, so they uptake water from the atmosphere. So they need to be protected, and if you don't, then the temperatures that you will see are quite a bit lower than for the binary phase diagram. And this was nicely shown in 2016 from a group from Clermont-Ferrand, by a group from Clermont-Ferrand. And they showed that you can already have depressions of like 8 to 10 centigrades if you have 2% of water. And 2% of water is not a weird amount if you don't dry your components. I've prepared mixtures in the lab that easily have 1 to 2% of water if you don't take care of drying. And this is also expressed in one of the later mixtures that I tried to make, ethylene glycol with choline chloride, a very common deep eutectic solvent, but we tried to do some calorimetry with it here in the IPC. The problem is that the compositions that I made never became liquid at the temperatures that I thought they might be. Admittedly, I'm quite close to the phase boundary, but I found that just being a little bit higher in water content actually gave completely clear mixtures. So I think that here it's also a matter of being just a few ppms extra or less, and it can already make a difference. So this is important to report. I think for all deep eutectic solvents, what is the water content, at least for the ones that are hydrophobic or have a hygroscopic group, like even hydrophobic ammoniums, they can absorb water, and this can still affect the phase behavior. So it's important to have this water reported. Then up to now, I've shown you mostly eutectic phase diagrams that are simple in the sense that the solids completely demix, and there are no weird complications when measuring the phase diagrams. But in practice, this is often not true. And one of the most annoying things from eutectic mixtures is that they are easy to supercool, which means that if you cool them down, they won't crystallize at the point that they should crystallize. Instead, you get a supercooled liquid. And this is why there are many DSC curves that are published in literature that are flat, where there is no exothermic crystallization visible. Instead, you get the glass transition temperature. This is also why initially in 2012 launched the term low transition temperature mixtures. I now don't use it anymore. I also don't recommend to use it anymore, but this is where it came from. So the fact that there is no eutectic transition, and I didn't want to call it eutectic. It's weird if you don't see any eutectic behavior to call something eutectic. And the supercooling can mask eutectic behavior. Often it's there, but you have to do some effort to actually achieve it. And this can be done by going up and down in a very small region in the DSC in temperature. But you can also use the addition methods that I described before, because if you add, you keep the temperature constant, so supercooling is not really an issue. And the centrifuge method also circumvents supercooling. Then another thing that can happen is that you have significant solid solutions, This is one of the other phase diagrams that I measured in 2018 and published in 2019. And here you can see that there are some points that are going down. And actually there are appearing two phase transitions. And that's quite a clear signal that most probably here there is a solid solution formed. And as you can see, the solidus phase boundary is not flat over the whole composition range. And this can also affect the shape of the liquidus phase boundary, also in terms of describing it thermodynamically. So this can give you some weird results as well. And then back to urea choline chloride. There is co-crystal formation reported on this system. It's very close to the eutectic point, so it doesn't really affect the phase diagram too much. But as you can see here, these black dots were prepared with the co-crystal. So what I did was preparing the eutectic mixture, heating it up until it was fully liquid, and let it crystallize again completely. Then I ground up those crystals that should be in the co-crystal form, and checked that also with XRD, and then made again the mixtures from that, and it gave a different phase boundary line. So the co-crystals are not always formed within the normal experiment if you use a DUC or melting capillaries. So sometimes these kind of sample preparation steps are necessary to get the real phase boundary, the real equilibrium boundary. And then another thing that's important that also happens within this phase diagram is polymorphism. So choline chloride has two polymorphs, an alpha and a beta form. It's about 78 degrees Celsius, I think. And that usually appears as a horizontal line in the phase diagram. Now, in principle, for the phase diagram, it doesn't really matter much, but for the description, it's important to also take into account the enthalpy of this solid-solid transition. So polymorphism is important to keep in mind when you're starting to describe your phase diagrams using thermodynamics. And then a last remark. This is also from ethylene glycol with choline chloride. It does corrode even stainless steel, and quite quickly. I was actually surprised by the speed at which this happened. This was basically overnight. And both the stirrer and some of the capillaries that were used, they were corroded. And yeah, this was also repeatable. And I also did it with some small parts of stainless steel from the workshop. And it's quite corrosive. So take care of these things as well when you do experiments. Then you can, if you have the phase diagram, describe the phase diagram using Gibbs excess energy models, or predict them if you don't have data and you have a nice predictive model. And I know you do this a lot in your group, but I will go over it quickly. I think it's important to note that the depth of the eutectic is mainly determined by the mixing behavior in the liquid, because it's in equilibrium with the pure solid or a solid, normally a pure solid. The main behavior where there is interaction is in the liquid, so there should be a good model to describe these excess properties in the liquid. Then usually this is a continuous function of composition, so there are no magic compositions in which suddenly there is a certain interaction that will deepen everything a lot. It's continuous. And this was also shown by MD, First Principles MD, by Barbara Kirchner and Azilu Padova, that's also located here. So if you have data but no eutectic point, you need a description that is a continuous function of composition, just a Gibbs excess model. And that can then describe your data and extrapolate to the eutectic point. And we showed in Eindhoven that this is possible with quite simple models, actually. You can use just a Rettler-Kister with 1 or 2 parameters, and usually it fits the data quite well. If you only use the first parameter, it even suffices only to use the solidus temperature. So if you cannot really do the full phase diagram because of limited time or because of all the issues that I described before, but you do manage to get a solidus temperature, then you can also just measure the solidus temperature and fit already using the single parameter Rettler-Kister to get at least an idea of the eutectic window. We saw also that in this description, it is sometimes important to take into account differences in molar volume using the Flory entropy. But it's not so important to take also into account the surface components using the Stavelman-Guggenheim contribution. It appeared to be negligible for the phase diagrams that we studied, even though they were showing quite a strong deviation from ideality. Then if you do not have data, of course, you would like to predict the phase diagram. And one of the approaches is SAFT, soft SAFT, PC SAFT, whatever SAFT is the best for the system that you choose. And I really liked this publication where you model the ethylene glycol colon chloride system and can describe it quite well using SAFT, which is parameterized from other measurements that are simpler, like density measurements. So it's kind of a semi-empirical approach because you still need to determine these parameters, but I think it's very valuable if you don't want to measure the whole phase behavior. Of course, for verification it's necessary, but now in the future we can just use these parameters, which is great. And another way is Cosmo. I also really like the presentation that was given in your group before by Rafael Pellegrini Suarez, which was great. And here I take one of the type 5 DESs that you presented before, which is actually by coincidence also overlapping with this publication from 1921. So there is actually some data there. And as you can see, if you overlap the two, I didn't have the description in Cosmo nor a table of the data, but you can see that it's quite well matching. And it's very nice to predict the SLE like this with just the information of the pure components. But we also heard from Rafael that the problem is that you the components, there is no 3D information saved. So for real accurate descriptions and having also spherical hindrance included, we still need molecular dynamics, which of course much slower, but this is at least a very good start. I like it, and we will definitely use it in the future too. So then finally, I would like to finish about these GIP success models by giving 3 recent reviews on modeling of deep eutectic solvents. I think most of them, at least together, they cover almost everything that was used to describe deep eutectic solvents up to now. And it's actually showing as well, since it's all in 2020, that this is a hot topic and that people are really trying now to understand this phase behavior that is behind the deep eutectic solvents applications that we see a lot. So that brings me also to the application side, the solvent side of the story. And I would like to show what I think is the most powerful part of the deep eutectic solvents. So first of all, it's conceptual. I think in 2004, what happened is that the whole community of ionic liquids, mostly, but also other communities, were made aware that you can also use solutes as solvents now by adding another component. And of course, people that were studying mixtures of ionic liquids were aware of this already. But a lot of other people weren't, and I think it's very valuable that the message is that you can just components that are solid at whatever temperature you want to work with them. You mix them and you can actually use them in the liquid phase. And this transition from solute to solvent is, I think, one of the main powers of deep eutectic solvents, and what's the most surprising for most scientists that did not hear about deep eutectic solvents before. Then another important thing is that if you have a phase diagram where the eutectic point is like at 0.3 mole percent, 0.3 mole fraction or half-half, then the concentration is very, very high, usually much higher than one can reach in a molecular solvent. And this gives you access to all kinds of very interesting applications. For instance, one of them could be polymerization of the deep eutectic solvent components, because they're so abundant. They're also very available for reaction, and you can easily polymerize them. And this is nicely described in the review that is given here below. And apart from polymerizing the components of the deep eutectic solvents, you can also use them to form another phase to do, for instance, micelle polymerization or making gels. It's actually good to keep in mind that the concentration of the components is always very high. So you have to have a good reason to use a deep eutectic solvent because it's expensive, basically. All the components that you add there They're there a lot, unless of course you dilute it again in a molecular solvent, but then the question is it still a deep eutectic solvent? So one of the approaches that I took during my PhD was searching for a problem where this concentration limit was the issue. And one of them is the extraction of volatile fatty acids from water streams, where they used mostly hydrophobic molecular solvents like hexane or cyclohexane to dissolve an extractant, in this case trioxide phosphine oxide, topo. Let's say topo, it's easier. So this topo was dissolved in a molecular solvent, but the limit of the solubility determined how well the solvent would perform. So I thought with deep eutectic solvents we can maybe extend this limit and go to much higher concentrations of this topo. And indeed we could. I made a phase diagram and I could reach almost half-half in terms of moles. So that was quite high. Then I applied it to the extraction, and to my surprise, the performance was actually not so good. As you can see here, if you transform these mole fractions to concentration in the liquid phase, the concentrations are indeed extended, but the performance, the distribution coefficient was much lower than you would anticipate from these molecular solvent solutions. And this is probably because the other component that we use to actually get access to these higher concentrations is inhibiting its function. So it's important to keep this into mind when you design a new deep eutectic solvent, that both of the components should be useful for the application, or at least not hamper it. This is of course important. Recently there was another publication also on topo, where they used malonic acid, and that worked much better for the extraction of gallic acid. As you can see here, it's much better than the benchmark, and they could actually extract higher amounts of this gallic acid salts from the water phase. So it can work if you choose the components wisely. Then the structure of deep eutectic solvents also is important for its function, but also to see where these interactions arise from. Because of course, if you describe the phase diagram with Gibbs access models, you know the total picture, so the bulk picture, but not which interactions are actually there in the liquid giving rise to these bulk properties. And structural studies of deep eutectic solvents do tell you this. And what we did recently, and that's submitted now, is study what the role is of this chloride ion in choline chloride deep eutectic solvents. And what we did is adding a little bit of water and see how this affects the chloride solvation environment. And what we saw is that if you have the neat ionic liquid, there is quite a bit of symmetry around the chloride ion. But as soon as you add water, this symmetry is disrupted, and you get a dip in the symmetry. So the most asymmetrical place is somewhere in between the neat deep eutectic solvent and a diluted deep eutectic solvent. And we could see that the symmetry would go up again when you put a high dilution, because water can then nicely rearrange itself around the chloride and again form a symmetrical structure. So it was nice to actually see these three different regimes of having a very symmetric part in the deep eutectic solvent, then have an asymmetric part in the middle, and again a symmetric part at higher dilutions. And this was done by chloride NMR. So we studied the line width of these peaks, and confirmed by MD. And it's a nice combination of these two techniques that show this re-entrant behavior of the chloride solvation environment symmetry. Then this was not included in this review, but there's a very recent review on the microstructure of deep eutectic solvents to understand its phase behavior. I, by the way, do not like this phase diagram where they show still the delta T1. Of course, that should have been a delta T2. But anyway, it's in terms of microstructure of deep eutectic solvent, it's a nice work that summarizes basically the important studies that were done up to now that highlight the interactions that go on in deep eutectic solvent on a micro scale. Then in our group, Katja Goloviznina is also developing a new type of force field. It's a polarizable force field that is transferable between different components. So it's not necessary anymore to, for every component, set up a separate force field. And it would allow to actually study these kind of microstructures, including the polarizability of the molecules itself. So it's not fixed charge, it's a polarizable force field. And this is, I think, submitted a few days ago, so I have it still here, the archive link, but it's actually submitted as well. And this is very exciting. I hope to actually see how this can contribute and combine with the experimental work that we're doing as well. And probably you'll read or hear more about this in the future. Then the last power of deep eutectic solvent is, I think, that there are known constituents. So unlike ionic liquids, which are usually synthesized as new components, they don't have to be approved anymore by the authorities or by industry. The people already know these constituents. So that is really nice for legislation and for applications. So if there is a very nice application that works very well with deep eutectic solvents, it's quite easy to implement it in real life. And I think this is also a great pro for deep eutectic solvents, as compared to newly synthesized components. So that brings me basically to a roadmap to using eutectic solvents, which is select first the components that match your application. Try to model this, or at least think about which components can help in doing whatever you want to do in the application. Then, as soon as you've selected the components, evaluate the liquid window at the temperature that you want to use it, or of course study a full solid liquid equilibrium. So that would of course be ideal. Then, if you want to call it deep, or if you want to evaluate whether it's deep, compare it to the ideal eutectic. But I have to say, it's not necessary to use deep eutectic solvents. I know that's a bit weird from a person that mostly worked with deep eutectic solvents, but any eutectic system can be used as a solvent phase. In my opinion, it's not necessary to have a deep eutectic. It's just a bit less surprising that you use it as a liquid phase, but it's still totally viable as a solvent. And then the last thing that is not said enough, I think, to the community, deep eutectic solvents are mixtures. They're not complexes at a certain fixed molar fraction. That means that if you use them, for instance, in aqueous biphasic systems, that one of the components can leach, that your composition can change, and that you can move out of the liquid window. And the same goes for reaction. We showed this esterification in the earlier publication. And if there is enough esterified product, you might out of the liquid window and actually not form complete homogeneous liquid anymore. So this is important to keep in mind always. Then what I think are the future challenges towards understanding deep eutectic solvents and the formation of actually deep eutectics is the accurate and fast prediction of the phase behavior in solvation. So find models that can actually do this. I know Cosmo is already quite far, and SAF too, but as Rafael also said, there are still hurdles to take in ionic components. It's still tough to completely model what's happening there, especially if there are also a lot of polarizable components there that form strong hydrogen bonds. And of course, we also need to know the physical chemical properties, the density, viscosity, conductivity, name it. It's important for most applications to know these things, and it would be nice to predict them as well. Then, in order to verify those models, or to develop them, of course, we need a lot of homologous series of systems and measure them experimentally. And this is what I think is great from what you're doing in your group. There's a lot of phase diagrams coming out at the moment, and it's actually fantastic because then we can see which things are determining how deep a eutectic is. And of course, what we're also after, because we're calling them solvents, is solvation. So how do these components, if they finally form a eutectic, solvate the solutes that you're interested in. And is this actually competing with, for instance, the formation of eutectic or not? I think these are important questions to answer in the future. And then, of course, how does the structure of the deep eutectic solvent give rise to this phase behavior? So these are, I think, the main things that are already known for quite a bit, but not enough to really fully predict what is going to happen when you put together two components that form a eutectic. And of course, there are many other things to think of, including reactivity. I'm not an organic chemist, but there are many reactions going on in deep eutectic solvents, both wanted and unwanted. And I think this is another chapter to look at as well. Then I came to the end of this presentation, and of course I did not do the work alone. So I would like to thank the people that are here at the ENS. Of course, first Margarita, that hired me here to do experiments with the colorimeters. That's actually great. And also Laura, who worked a lot with me during my PhD, and also after moved with me to Lyon, but now is already back in the Netherlands as an assistant professor at Maastricht University. And Guillaume is doing a lot of experiments currently on deep eutectic solvents too in the lab. He makes it smell sometimes a bit, but that's great. It's really nice to have him on the team. Then there's also a theoretical part that is mostly doing molecular dynamics. I told you about Agilio before, but also Katja, a PhD student of Agilio, that developed this polarizable force field, and Oliver, that I knew already before from conferences, but now also had the pleasure to work with together on the MD side. So with that, I would like to thank you for your attention, and thank you again for the invitation for this lecture. I hope you enjoyed it.
Thank you very much, Adriaan. It was a very interesting review on eutectic systems, on the deep eutectic systems. And let's go for some questions. Does anyone have questions? Well, I
do, Maria.
Perfect.
Nobody. Oh, Anna Power. Start by Anna Power. Oh, no, it was not Anna Power. Sorry. I don't see any right hands. George.
Yeah.
Thank you, Adriaan, for this.
Ooh, this is very soft. Wait a second, I will put you a bit louder. Yes, say again.
Are you listening now? Okay. Thank you for your nice presentation. I have some, I agree with some points of view, and you talk about salvation. I'm quite curious about how do you think that if you increase, several people have been working with Ecole's deep eutectic super liquid systems where you have two phases and in water. And you explained that you can have three different types of structures using deep eutectic. Do you believe that this structure, you have three types of solvation structures in water? Do you explain about that? Do you think that we can have more types of solvation if you have other types of deep eutectic solvents? So you explained that you have in water, you can have three types of structures.
It's not exactly three discrete structures. So these are regimes that are basically marked by this minimum in the symmetry for the chloride anion. So I have to also say that this is all only for the chloride anion. We focused on that. So, yes, but there is a continuous function. It's not like there are three specific shapes of that surround chloride in diluted system.
But you have, it's clear the existence of three different regimes.
Yes.
Do you believe that if you change the chloride, you will have the same regimes, or it will be completely different? Because we have other type of deep eutectics that do not use chloride, and I'm quite curious about.
Well, of course, chloride is a very small ion, so this also gives rise to a lot of interactions that it can have with other components. So if you have a much fuzzier ion, or just not a charged component at all, of course this behavior might not be reentrant at all and just be smooth. That's possible. It can also be the opposite. But for the chloride is that the water really wants to coordinate with this chloride as soon as you add a bit in the deep eutectic solvent, and actually competes with the components of the deep eutectic solvent. And as soon as the water basically takes over, it's the other way around. So it gets expelled, the deep eutectic solvent components keep on being expelled from the chloride environment and are basically separated from each other. And this is something that I would expect for most salts. What is unclear yet is how the hydrogen bond donor would affect this. In the systems that we studied, they had quite a similar effect. So if you change the donor, so not the salt but the donor, we didn't see many strong differences in this reentrant behavior. But we didn't study other ions which might really affect the polarizability of this component. So I cannot really give a prediction there.
When you study, I'm really interested on that, for sure.
Yeah, of course, it would require other NMR studies. So now we did chloride NMR, but you can also, for instance, do bromide NMR or nitrogen NMR if you have nitrates, etc. So these are possibilities definitely in the future to expand the ions that we study. Yeah. But we didn't do it yet.
Okay, Professor?
Adriaan, thanks for your wonderful lecture. It has been very interesting to follow it. And well, I already knew that you and I agree in many things about the eutectics, but it's great to see that people are coming around and coming to the same conclusions that somehow through other ways we also reach sometimes. I'm really happy to see that you are enjoying yourself and having great fun doing calorimetry there in Lyon. Mm-hmm. But that's not about calorimetry that I'm going to ask you. It's about the deep eutectic, in particular the ternary eutectic systems. And it's great that George asked you about these things in another perspective. If I understood correctly, your vision of eutectics is, well, something that has a lower melting point than an ideal solution, but the deep eutectics, the eutectics in general, they have melting points that are lower than the pure just because you mix two things point. Now, if you also agree, I believe that you can have eutectic systems, not just with two, but with 3, 4, 5, or if there's many compounds as you want, right? You are not restricted to binary mixtures.
No, not at all.
Okay. If you are not restricted to binary mixtures, and as you showed, for instance, when you add water, you have a further decrease on the melting point, right? Mm-hmm. Why do people keep asking or keep saying that when you add water, you may no longer have a deep eutectic system? If you add water, you are just having a ternary mixture where water is one of the compounds, and that would be also a ternary deep eutectic, right?
Yeah, no, I completely agree. So okay. This is something that we don't disagree on. I'm just saying that if you want to measure the binary phase diagram,
I agree.
That you should keep into account that it might be a ternary one that you're actually measuring. And this is important to keep in mind. And a lot of people that do measure phase diagrams because they're doing an application, they're not that careful with that. So it's just making that note that it's important to keep track of all the components that are there because they might affect the phase behavior in the way that a ternary system does, or a quaternary, or whatever.
Yes, I agree with you. And that was not about the binary, it was really about this question that keep coming up in reviews to my papers, or sometimes when you meet people. But if you have water there, you no longer have a deep eutectic. Well, it's a ternary deep eutectic. What I won't destroy the compound's ability to decrease. It may decrease more than, but it's just a ternary eutectic. I fully agree with you.
Yeah,
And
but
we
of
have to
course,
explain this to people, I guess.
yeah, but the more components you add, the messier your system gets.
Oh,
this
absolutely.
is also true. And so what I do understand is that people say you wanted to combine these two functionalities, and now you add water. And how does that interact with these functionalities in the application that you have in mind? But
Yeah.
indeed, it's not like you destroy the eutectic. No.
No. Thank you.
Okay, thank you. Some more questions. We have André. André?
Yeah, sorry. Yeah, Adriaan, thank you very much for your presentation. I fully agree with most of the things you have said about the Eutectic solvents and the chemistry behind it. I'm just wondering about the part of the reusability of these solvents. When you use in some chemical reaction, wherever, and you have to do some downstream processing, and then you want to recover this Eutectic solvent. And if we compare with ionic liquids, is there any advantages in using Eutectic solvents and how to recover it?
I would say this is a very interesting question. That's first. And something that most people don't look into at all, including myself. So I'm not judging here. But yeah, of course, it's very interesting to see what Eutectic solvents can dissolve and what you can do in Eutectic solvents. But in the end, for industrial application, indeed, you won't escape downstream processing. And I think because you're using two components and not just one, you make your life more difficult. Exactly. Especially since you want to keep a certain ratio and a certain liquid window. So sure, it will be more difficult. So that's also why I say if you want to use Eutectic solvents, you have to be quite sure that you want to use those components. Because if it's just because you know that it forms a eutectic, that's not enough, because you might get a hard time whenever you want to do purification of this Eutectic solvent or extracting back whatever you put in there. So this is difficult, and yeah, of course there are many standard techniques that you can still use. You can use liquid-liquid extraction, but you have to be sure that you won't extract one of the components more than the other, and this is difficult.
But for instance, with your experience about these different structures that Eutectic solvents can have in, for instance, water solutions, if you have any experience about the part of the reusability, if somehow there is a structure that is better than the other to the recovery, for instance.
I wouldn't go that far. I think that the structure is more a result of the composition than the other way around. So yes, I think this,
for instance, I would say, comparing, for instance, the recovery of a pure DES, that is a molecular structure, or the recovery of aqueous solution of DES, that there's a completely different structure, and somehow these differences, if it influences the recovery process, somehow some structure could be better than the other for the recovery to maintain this molar ratio.
I understand where you want to go, but I do think that these structures are not maintained at any moment, basically, unless you keep the composition constant. So if you would like to do a recovery step and you change the composition, the structure will change as a result of that and not the other way around. So I think an aqueous solution of Eutectic solvents might not be easier to recover. It might even be harder because you add even a third component, which is water. So if you really want to recover the streams, you have to find a way of getting out of the Eutectic solvent what you put in before. And that's why I really like these applications with polymerizations, because there you actually use one of the components of your eutectic solvent to create a product, and it's automatically separated from this eutectic solvent phase. So you don't have this problem that you describe here. I think to use it as a common solvent, eutectic solvents have a lot of problems because it's hard to distill them, it's hard to extract them, it's hard to filtrate them, and so it's the normal operations in industry are not easy on the eutectic solvents. I think it's definitely possible, and you can find ways to achieve it, but it's not an easy process. And I think different structures in the eutectic solvent don't give rise to an easier separation or a harder separation. It's more the other way around, that the structure is a result of the situation you're in.
Okay, thank you.
Oh, I lost sound of Monia.
Yeah, I think Nicholas raised his hand.
Yes, hello. Hi, Adriaan. Thank you very much for this talk. I was particularly interested in your results with your topo extraction and comparing to normal organic diluent. I think a lot of solvent extraction assumes that the organic diluent is inert. Therefore, the extractant behavior is minimally impacted by the diluent itself. This is obviously very different when you have a eutectic system that is highly hydrogen bonded. So how do you see this impacting solvent extraction, well, the incorporation of these extractants into eutectics? Do you see this as a negative thing or possibly increased selectivity, or what's your opinion?
I think both can happen. So as I showed in my own example, it didn't help me. It was a negative thing. So the hydrogen bonds that needed to form between the thing that I wanted to extract, components. So this was not a good strategy. But if you can form a eutectic in a different way, so for instance, not via hydrogen bonding, or you extract something that doesn't need to go into the eutectic solvent via hydrogen bonding, you can still have a positive effect. So it depends all on the components that you use and on the functionalities you include. And you need to kind of form the eutectic by one type of interaction and do the extraction by the other. Or use two of the same functionalities that both are beneficial for the extraction. So I think it's definitely possible to use eutectic solvents for extraction purposes and not have them interact or interfere with the application. So
in your opinion, for example, as you would move from toluene or hexane as a diluent to a system presenting strong negative deviations, do you think that you would see a systematic increase in your extraction of your compound? I think it's not that black and white. So as soon as I said in the title, there was some nuance, but okay. So if you have this strong negative deviation because of the same interaction you have with your solute that you want to extract, then it will be it will be a worse performance with a stronger negative deviation from ideality in the eutectic behavior. But if this is not the interaction that is steering this depth of the eutectic, then you can also make it better. Again, it depends a lot on the component that you choose. Yeah. Super, thank you very much.
Thank you, Nico. So some more questions? Well, I have one question more related with the experimental part. Adriaan, did you already try the annealing technique?
The annealing technique?
Yeah, I'm not sure if you are familiar with. It's something they use for DSC for some compounds that have problems with crystallization. They just put the compounds in the low temperature, fixed temperature, like -40 or something for weeks or months, and then just increase, you know? Okay,
yes, I've done it, yeah.
For eutectic systems, eutectic mixtures.
I did it for one that was extremely problematic in my case, which was this ethyl ammonium chloride with glutaric acid. And I kept it, yeah, it was at -20 or something for 2-3 weeks. But it didn't help. It was, yeah. So, yeah, maybe we need bigger freezers, maybe the ones where they will keep the corona vaccines in that -80 for a long time. But the freezers that we had at our disposal at that time didn't help for those systems. For other systems, they do, obviously. I mean, if you keep it in the fridge or the freezer for a long time, this crystallization might happen eventually because it's a stochastic event. So, of course, if you give it time, it helps. But not for all systems and not always. And then, of course, you also have to be very sure that the DSC pen you crimp is completely sealed. Yeah. This is also an issue that I had before, that I went up and I saw a nice peak at 0 degrees and I was like, yeah, okay, never mind. So yeah, but annealing is definitely a technique that you can consider too. Yeah, sorry, I didn't include it, but definitely.
Okay, thank you very much. So if there is no more questions, I just want to thank you again. It was very nice. And I guess Professor wants to say something, maybe?
No, to thank Adriaan as well, just to say goodbye. It was great to have you here with us, sharing your work and the results, your thoughts on this subject with us. And I would summarize your presentation with a very simple sentence, that is, if you can do it with a simple system, just with one compound, don't use two compounds, don't use adhesive if you can have a solvent or any other. Am I right?
I think that's right, yeah. But two components can do the job too. And sometimes sure. Better, sure. So don't throw them away.
Only use them if they can do better than just a single one.
Definitely. And also evaluate this. I didn't add that in the presentation, but it's important also. Check the performance of the separate components first. Yeah, but okay. Absolutely. Thank you very much for the invitation. Thanks, and for this platform as well. I've never did a presentation like this, and it's a nice new experience. So one positive thing from this weird situation that we're in. Yeah.
All right. Bye.
Thank you very much.
Thank you very much, Adriaan.
Goodbye.
Thank you, Adriaan.
Thank you, Adriaan.